But that's a little different than the one we just did. For that multiplication, I'm doing e to the x times e to the negative x, right? That's what I'm doing? Now, I'll remind you of something below this. What if I asked you to do x squared times x to the third? What would you tell me? Add the exponents, right? Because they have the same base, you add the exponents. Do these have the same base? Add the exponents. What's x plus negative x? 0, right? So that's e to the 0. Agreed? Which is 1. Anything to the 0 is 1, except 0 to the 0, but that's a different story, right? So do you all agree that that second multiplication is going to give me 1? Yeah. All right. No questions? All right. This is all algebra that I'm doing here, but I'm taking my time through it because it's not algebra you see every day. All right. And then I'm going to do my inner one. Here to here. Same thing. And I didn't point out on the last one, when we did this times this was a positive term and this was positive, right? So when they multiply, it's positive, and that's why I got 1. This one to this one, they're both positive, so my answer should be plus. And then, again, same multiplication, so it's going to be plus 1. And then what about the outer one, like this? E to the negative 2x. E to the negative 2x. So it's plus e to the negative 2x. Same thing. You're adding the exponents. Negative x plus negative x is negative 2x. Pardon? These do not cancel. They would have to have the same exact thing up here, 2x, 2x, and one of these would have to be minus. Okay, 1 plus 1 is 2, right? I can do that. So this is e to the 2x plus 2 plus e to the negative 2x. All right, that's what I get when I expand this right here. Okay? How would things change if I expand this one? Yeah, let's see. I'm not going to rewrite the whole thing, okay? All I'm going to do here is I'm going to change this to minus and this to minus, all right? So we're doing this one right here, okay? Would the first multiplication change? This is still positive and positive, so we'd still get this, right? When I do this one times this one, we'd still get 1, but it would be a positive times a negative. So it'd be a minus, wouldn't it? And then the inner one, I would have a negative times a positive, which would give me another minus. And then the outer two, I would have a negative times a negative, which would be plus. So the only difference here is that we're going to have minus 2. Do you all see that? Other than that, it's the same game of exponents. All right, I'm ready to rewrite this here. So this is going to be 1/4 parenthesis everything that this turned into, which was e to the 2x plus 2 plus e to the negative 2x. Close it off. Then I have minus 1/4, right? Minus 1/4. And then everything that this turned into, which was this one right here with the little red negative 2 right there. So e to the 2x minus 2 plus e to the negative 2x. May I erase? This is gone? Okay. What next? Distribute the negative, sorry, not the negative. Distribute the 1/4 here. 1/4 there. It's actually negative 1/4, so it's going to change the signs. And I think we're going to be there right after this. Let's see. So 1/4 times that is this. 1/4 of 2 is a half, right? And then plus 1/4 e to the negative 2x. And now we start getting some negatives. So minus 1/4 e to the 2x. Then what? Plus a half. And then finally minus 1/4 of e to the negative 2x. Do y'all see what happens now? Lots of canceling now, right? Lots of things go away. This and this, where is it? There it is. Those are like terms because they have the same base, same exponent, right? E to the 2x. One of them's positive, one of them's negative. They cancel exactly. And then this one right here and this one right here go away. And the only thing you're left with is 1/2 plus a half, which is 1. That's the right-hand side, right? Check. I've shown that that is an identity. The point of this problem was just to get you familiar with working with the e's like that, and how when they multiply you have to pay attention to the exponents and how they combine. Any questions? All right. Moving along. There are a lot of identities for the hyperbolic trig functions, but we're not going to get bogged down with them. I'm just going to point out some of the more important ones. And these are the types of things where you just need to know that they exist. It may not come up in this class, but it might be in some weird, differential equations class or something down the road where all of a sudden you've got these hyperbolic trig functions, and all of a sudden someone turns, this into this. You're like, what happened? Well, it's an identity. You may not remember it, but it's, that's what's going on there. So you just want to be aware of these things. So we have this first identity that says that if you take hyperbolic sine and you plug in a negative value, it's the same as plugging in the positive value, but you have to change the sign to negative. So does anyone remember what this property is called when you plug a negative into a function? It's the same as taking the function without the negative and just changing the sign? I'll give you an example of a function that behaves like this. Well, I'll give you two examples. Sine x. Here's another example of a function that does that, x cubed. See, if I plug in, this one's easier to look at. What happens if I plug in -1? Forget this one for now. What happens if I plug in -1 here? I get -1 cubed, which is -1. But that's the same as me taking that same function and plugging in +1, right? But making it negative. So this would be -1 cubed, and that would give me -1. So they're both the same, right? Does anyone remember what this property is called? Odd. This means the function is odd. And if you graph them, they're reflections over the origin. So like if I take x cubed, it looks like this. If I reflect it this way and then this way, it will just land right back on top of itself. That's called reflection over the origin. All odd functions behave that way. Sine is another example of an odd function. Let me just take the first period of this. If I reflect this over the y-axis, and then over the x-axis, it will appear like this. And so it'll land right on top of itself. So that means that the hyperbolic sine function is an odd function. What about this one? That means it's an even function. And that means it's a reflection over the y-axis. And if you remember what this cosine hyperbolic looked like, we said it looked kind of like a parabola. If I take it and I just flip it over the y-axis, it's itself, right? Was cosine an even function from pre-cal? Yes, it was. If we take cosine, I know I'm like getting all over the place here, but if I take the cosine function, which looks like this, and let me just draw this way also. If I take it and I just kind of, pivot the whole thing around the y-axis, it's going to land right on top of itself. It's the same function. So this means it's an even function. This is the identity I just proved. How do you get this identity? Well, you could write it all out, couldn't you? With all the e's and stuff in there? Yuck, though. That's pretty nasty to do it that way. Does anyone have a more efficient way to go from this identity to this one? Pardon? Let me ask you this. You remember in pre-cal, you all said that this was important, right? You agreed with me that that was pretty important? But weren't there two others? Do you remember those as well as you remember these? Some of you do, some of you don't.
Could you put cosine and sine over each other?
Where, here? Just change it into what it is? Like sine over cosine? You could. But I'm going to try and show you a more efficient way of doing it. I'm going to take you back to pre-cal to do it. Say, everyone's got this one? Everyone knows there's two others, right? but we don't remember those as well. So the trick to do them is to get one of them. The first thing you do is you divide everything here by sine squared x. Okay? So what would happen if I divide that by sine squared x? I get 1. What if I divide that by sine squared x? That's cosine over sine, which is cotangent, and it's squared. So this would be plus cotangent squared x equals, what's 1 over sine squared x? Cosecant squared x. And if you look in your formula sheet, this was one of those other 3. And how do you think I get the other one? Divide everything through by cosine squared. So what would sine over cosine squared be? Tangent squared x. What would cosine over cosine be? That would be 1 equals 1 over cosine, which would be secant squared x, right? So those are the 3, and that's how you get them. So with that, how do you think you could get this? Divide each one of these. This is the one we proved, right? We proved this one. We just take each term and let's say divide it by, well, how would we get 1? Cosine squared. So take this and divide it by cosine hyperbolic squared x. Divide that by cosine hyperbolic squared x. Take that, divide it by cosine hyperbolic squared x. Understand? We get what? 1 sine over cosine hyperbolic, tangent hyperbolic squared equals 1 over cosine hyperbolic is secant hyperbolic, so it works, right? With me? Okay. And then the last one we won't prove. I think you have a homework problem like this one. Like one of these two, I believe, is a homework problem. And let me just tell you, it's not as straightforward as the one that I proved here, because here the left side was obviously the easy, like the side, sorry, not the easiest, the more complicated side. So you started with that and turned it into 1. For this one, if you look through my homework solutions for help, you'll see that what I had to do was write out the left side first, and then write out the right side, and just kind of made them meet in the middle. But that means I'm going to have to turn this, right? I have to take this and I have to turn that into what? What's the definition of that? Let's see if you can write that down. What's the definition of that in terms of the e's and stuff? I'm saying turn it into that formula. 1/2 e to the x plus y. Sine is subtract. E to the negative x plus y. Do you see the argument? The argument of this hyperbolic function is x plus y. So when you go into the formula, you're replacing, instead of the x, you're replacing it with the x plus y. Understand that? And then you got to keep working with this. And my hint to you is obviously I do it in the homework solutions, so you're going to see how this is done. But I'll just remind you, that's the same as e to the x times e to the y, isn't it? And so I promise you, if you start working with this side now, that means rewrite this one as 1/2 e to the x minus e to the negative x in parentheses times 1/2 e to the y plus e to the negative y in parentheses plus that. And you start foiling all that out and multiplying it all out, and things start canceling and going away, and all of a sudden, you'll get this over here, and it'll work, okay? So enjoy. It's fun. It's good exercise. And we move on. Those are the 6 hyperbolic trig functions. And with those 6 functions, they have derivatives. And here they are. Right? For these 6, we now have the derivatives. Do they look familiar? Yeah. They look pretty damn oh, sorry. I'm trying not, I should. Okay. Everybody gets a 1-point bonus on the first exam. Every time I cuss, I'm going to give you a 1-point bonus. I'm really going to try not to cuss this semester. You're going to be in, you're going to, I know, right? Y'all are going to start upsetting me. What the? Okay. So these look a lot like the derivatives of the pre-cal functions, right? The traditional sine, cosine, tangent functions. The derivative of sine of x is cosine x. Derivative of hyperbolic sine x is cosine x, or cosine hyperbolic x. This one's a little different, right? Yeah, we're used to seeing negative sign for the derivative of cosine, but for hyperbolics, it's not. I wonder why. Oh, well, we'll just check why. Let's see. This is the definition of the hyperbolic cosine function, right? That's hyperbolic cosine. What's its derivative? Is that okay for the notation for derivative? All right, well, I have a constant out front, which when I take a derivative and there's a constant out front, it's just going to come along, right? So it's going to be the derivative is 1/2. And then I have two separate terms here. I can differentiate those piece by piece, term by term. So derivative of this is itself. And then this one, derivative is itself, but then you've got that negative x up there. So that's going to pop a -1 out. It's going to make that plus and minus. So it's going to be this, right? You recognize that? That's hyperbolic sine. So it's exactly hyperbolic sine. It's not off by a negative or anything. Got it? So I just verified that the derivative of this is this. And you could go and do the rest. I'm not going to. I'm not going to ask you to. There might be something in the homework for you to do, but I'm not going to do any more of those. You get the idea, right? If you were asked to verify that this was true, you'd have to write out the definition of this and then take the derivative. And that would require a quotient rule. And it would, see where it goes. All right. So let's now that we have those, right, and those were all listed on page 5, reference page 5, formulas 13 through 36. You've got all those. Now let's just clean the slate. Let's act like we've got some function. We want to take its derivative. All right, here it is. I want the derivative of that. So what do you see happening here? See a product. Yes? Everyone see the product? Your product is happening right here. So you've got to do the product rule. And so I'll take the derivative of this, which should be pretty clean, right? Times this plus the derivative of this. Now, how is the derivative of this going to look? It's chain rule, right? You have a function inside of another function. You've got the e to the x that lives inside of the hyperbolic secant function. So just remember the chain rule there. So let's do it. Y prime equals, you said the derivative of this one, which was 1, times the other one, plus, right? Product rule says plus. The derivative of secant hyperbolic of something. And I just scroll up real quick here. The derivative of secant hyperbolic of x was negative secant hyperbolic of x tangent hyperbolic of x, yeah? So the derivative here should be minus, I'll put it in parentheses, minus secant hyperbolic of e to the x, not x, right? Because the argument of this function is not x, it's e to the x. So secant hyperbolic e to the x, then times tangent hyperbolic of e to the x again. And then you're done with the derivative of secant hyperbolic. You have to go inside and take derivative of e to the x, which is itself. So that gets tacked on to the outside here, right? And then you have to finish off the product rule and multiply it times the first function, which was x. So you've got another x tacked on here. I'm going to close my parenthesis. Yeah, we can clean it a little bit, though. Secant hyperbolic e to the x minus x e to the x secant hyperbolic of e to the x tangent hyperbolic e to the x. So I just slid the x and the e to the x out front here with the negative, and that should be good. I could go one more step if I wanted to. I could notice that both of these terms have a secant hyperbolic e to the x, and I could factor it out. But that really wouldn't get you more It wouldn't make like any more headway than this is right here. We're not setting it equal to 0 right now, so I would be satisfied with that. Good? Okay.